This will be a short video on quotient spaces of vector spaces, very similar to the quotient groups or factor groups that we studied in group theory. Let V be a vector space over a field F and W be a subspace of V. The quotient space V mod W is defined exactly in the same way we defined the factor group of G mod one of its subgroups. Well, you know that V is an abelian group under addition, and therefore W is a normal subgroup, and so V mod W is certainly a group under the operation of coset addition. So we're not going to prove that again. You know this is a group under, let's write coset plus. I've indicated it with a red plus. So we have our abelian group. We would need to define scalar multiplication on it, and that's easy. Let's let A be in our field, and then we'll say A times the coset X plus W will simply be AX plus W. And since V is a vector space, the scalar multiplication, all 5 properties can be easily proven. Recall exactly what X plus W means. It's the coset containing X. In other words, it's the set of all X plus the W's in W. And therefore, if X plus W is equal to W, that happens if and only if X is in W. The operation in V mod W is, well, this is exactly the same as in group theory. We used a star here instead of a plus. I've just turned it into a red plus because it's a vector space. If we add 2 cosets, we simply add their representatives. And this operation is well-defined. Let's recall what well-defined means. It's very important in the context of factor groups or quotient spaces, because we could represent a coset by X plus W, but we could also use any vector in that coset to stand outside and represent the coset. So if this is true, and if Y plus W is equal to Y prime plus W, we have to be sure that X plus W, and then I need my red plus, plus Y plus W, adding these 2 cosets, is the same thing as we get if we have X prime plus W plus Y prime plus W. And you can go back to our your notes on group theory, and you see exactly how we prove this. The operation is well defined. It doesn't matter which representative you choose to stand outside and use when you are adding cosets. One other thing I see that I forgot to mention that's worth remembering. Remember, if X plus W is the same as Y plus W, if 2 cosets are equal, that means that X minus Y is an element of W. And this is real important. We'll use it in the proof that we're going to do in the next slide. Now we would like to find a formula for the dimension of V mod W. So let's let the dimension of V be n and the dimension of W be m. So we're going to start by let this set, let it be a basis for W. So let's see, we need m linearly independent vectors. Let's call them V1, V2, up to v sub m be a basis for w? Well, we know that we can extend that basis to a basis for v. So let's do that. Extend to a basis for the entire vector space v. So let's call it beta equals, and we have our v1, v2, up to v sub m. And then I'm just going to, not necessary, but I'm going to change color. Now I'm putting more vectors in, more linearly independent vectors, v sub m plus 1 up to, and since v has dimension m, we know that we need n linearly independent vectors for a basis. Okay, so now there's a basis for v. And what I want to prove is this. I'll write claim. I claim that this set, with the new vectors that we put in, v sub m plus 1 plus w, that coset, v sub m plus 2 plus w, and on up to v sub n plus w, that those cosets, n minus m of them, I claim that that is a basis for the quotient space v mod w. Well, since beta spans the entire vector space, we know that v1 plus w, v2 plus w, dot, 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 all the way up to v sub n plus w certainly spans v mod w, because those are the vectors that span all of v. But remember that the v sub i's, where I is less than or equal to m, those are in w. So we can say since v sub I is in w for I equals 1, 2 up through m, and w is the identity, it's the zero vector, so to say, for v mod w. We know that v sub m plus 1 plus w up to v sub n plus w, we know that this spans, let me write span back here, sorry, that the span of that smaller set of cosets is definitely equal to v mod w. We have a spanning set then, and so all we need to prove now is, let's write, we must prove that this set v sub m plus 1 plus w, that these cosets, n minus m of them, are linearly independent, that this set is linearly independent. So we'll do that on the next slide. So to show that this set of n minus m vectors, or cosets, is linearly independent, we pick some scalars. Let's suppose that a1 times the coset v sub m plus 1 plus w plus a2 times the coset v sub m plus 2 plus w plus, and now this will be a sub n minus m times the coset v sub n plus w is equal to the zero vector. But the zero vector in v mod w is w. So we are supposing that this coset on the left is equal to w. When I say coset, I mean that we will use the fact that it is a vector space and rewrite this as, this implies that A1 V sub m plus 1 plus A2 V sub m plus 2 plus plus A sub n minus m V sub n, that plus W is equal to W. Well, if we have this vector, if its coset is W, then we know that that vector is in W. So this implies that A1 V sub m plus 1 plus A sub n minus m V sub n is an element of W. Well, remember when we first started, the first line that we wrote was we picked a basis for W, m linearly independent vectors, and they were the set V1, V2 through V sub m. This is a basis for W. Well, that means that if this vector is in W, then it can be expressed as a linear combination of these. So let's do that. And you see we get a linear combination of V1 through Vn equal to the 0 vector in V. Well, that is V1 through Vn was the basis for V, so this implies that B1 equals B2 equals all the way up to B sub m, including A1, A2, up to A sub n minus m, that all of those n scalars must be equal to 0. In particular, these are equal to 0, which were exactly the coefficients of the cosets that we wanted to show were linearly independent. So we can now say that this set above, V sub m plus 1 plus W, that coset, V sub m plus 2 plus W, dot, 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 up to V sub n plus W, that is linearly independent. We already know that it scans the the quotient space, and so this is a basis for V mod W. And we get our result, that the dimension of the quotient space V mod W is n minus m, giving us the dimension of W plus the dimension of the quotient space V mod W is equal to the dimension of V. So we'll look at an example where V is the Cartesian plane, r squared, and W, its subspace, is the set of all ordered pairs where the y-coordinate is 3 times the x-coordinate. In other words, it's the span of this set, the span of the ordered pair 1, 3. So we know the dimension of W is 1. Well, what is a coset of W? It would be an ordered pair plus W. And what would it mean for something to be in that coset? Well, let's just take x comma y and say it is in the coset a comma b plus w. Well, that would mean that xy minus ab is in w, or x minus a comma y minus b is in W, which would mean that y minus b is equal to 3 times x minus a. Now, look at that. Compare that to up here. W is where y is equal to 3 times x. In other words, it's the line passing through the origin with slope 3. Look at this. Its cosets are simply vertical horizontal translations of that line. In other words, they are lines parallel to it. So the cosets can be thought of the lines parallel to the line y equals 3x. The quotient space V mod W can be viewed geometrically then as the set of lines parallel to y equals 3x. We know that the dimension of V is 2, the dimension of W is 1, so we know then by our previous theorem that the dimension of the quotient space is equal to 1. And in fact, it is spanned by this. V mod W is equal to the span of the point 0, 1, or the ordered pair 0, 1, plus W. Notice that gives us, if we multiply by a constant, then we multiply by any scalar, b, let's say, we have 0b plus w. And that would be the set of all x, comma, 3x plus b. And you see that that is a line parallel to the to y equals 3x. I didn't want to let the semester end without bringing you back to the first isomorphism theorem. It's exactly the same as it was in group theory. Let V and Z be vector spaces over a field F, and T be a linear transformation from V to Z. Then, the quotient space V mod n of T, the null space, is isomorphic to the range of T. The isomorphism is, we'll use psi like we did in group theory, maps V mod the null space to the range by psi of this coset of the null space, x plus n of t, is equal to t of x. It's exactly what we did with groups, except we called the null space the kernel. We called t phi. We called r of t the image of t, but it's exactly the same. We proved the first isomorphism theorem for groups, and so we know, because we've proven it before, as groups, we know that V mod the kernel, or we're using a different word now, the null space, is isomorphic to the range of T as groups. And we just define scalar multiplication as follows. For A in our field F, the field over V, we define A times one of the elements here, x plus n of t, one of the cosets, as the coset ax plus n of t. And defining scalar multiplication that way makes V mod nt into a vector space, as we've already seen, and it is isomorphic to the range of T, which we proved when we studied groups. Review for a second what we had to prove in group theory. We had to prove that psi is a well-defined mapping. In other words, if we were to use a different representative of the coset, that psi would map the coset to the same image, t of x. We proved that. You can look back in your notes and see. We'd need to prove that psi is linear But we called it a homomorphism. That just meant it preserved the operation, and that's what linear means in the case of the operation of addition. And we needed to prove that psi was 1-to-1 and onto. The proof is exactly the same, so I'll just say done. We've already done that. What this means is that if you find a linear transformation from V to Z, especially if it's onto Z, and you can identify the null space, then you can know that V mod n of t is isomorphic to Z. For example, if T is mapping Rn, n space to n space, and it takes an ordered n tuple, and it sends it to, well, it zeroes out the last n minus m coordinates and makes them all 0. And it just sends it to this here, which really we could identify this as Rm, as m space. The range of T is equal to the span of, let's use our standard basis vectors, E1, E2 through E sub m. Those are all n tuples with a 1 in the position indicated, like E2 has a 1 in the second position. So we see that the dimension of the range of T is clearly m. We can really identify the range of T as Rm, m space. Now, what is the null space? Notice it makes no difference in here what these last n minus m coefficients are, or coordinates, because it's going to send them all to 0. So that tells us what the null space is. The null space is the span of E sub m plus 1, E sub m plus 2, out to and including E sub n. We see that the dimension of the null space is n minus m. In fact, we could identify the null space in our minds as Rn minus m. This gives us, by the first isomorphism theorem, that Rn mod Rn minus m is isomorphic to Rm. So that was a pretty simple example using the first isomorphism theorem. R10, in other words, mod R6 is isomorphic to R4, for example.